right, so today we're going to talk about one method for solving non-homogeneous first-order linear differential equations with constant coefficients. So we saw if we have a sub n, nth derivative of our function plus a sub n minus 1, y n minus 1, plus dot dot dot, a1 y prime plus a0 y equals g of x. So this g of x is what makes this differential equation non-homogeneous. When we don't have not equal 0, then we have a non-homogeneous differential equation. In section 1, we saw that we need two things to solve this. So we need to solve the associated homogeneous equation. To find the complementary function. And we say y sub c. So the solution to the associated homogeneous differential equation is the complementary function. So we just solve this thing equal to 0. And then we need to find any particular solution to the non-homogeneous equation. And we'll call that one y sub p.
Mr. Beamer, is it possible to pick up my quiz before the weekend to go over stuff?
Yes.
No, but Beamer.
That's like Stephen's average score.
So our solution is then y equals the complementary solution plus the particular solution. So we've done some work already finding our complementary solution, finding our solutions to our homogeneous differential equations. Now we're going to talk about one method for solving non-homogeneous differential equations. So for our method, which we call undetermined coefficients, what we do is we make say a guess, but it's more of a conjecture, an educated guess. About the form of the solution, y sub p, based on the function g of x. So g of x is going to need to be particular kinds of functions in order for us to use undetermined coefficients. So to use this method, our coefficients a sub n, or I'm going to say a sub 1, a sub 2, a sub n, must be constant. So we have constant coefficients. And g of x is, and we have a list of types of functions. A constant, a polynomial, an exponential function, a sine or a cosine, or any finite sum or product of these. Any guesses as to why? So we're solving a differential equation. We have multiple derivatives involved. Why our functions would need to be like would need to be in this list? Any guesses? Well, yeah, they're nice. They're generally nice functions. Yes, that's a good thing. So these are functions where if we take the sum of the function and some of its derivatives, we get the same kind of function. The derivatives of a polynomial are polynomials. The derivatives of exponential functions are exponential functions. The derivatives of sines and cosines are sines and cosines. And if we multiply them together, we get multiples of those things plus some other things. But they're all, the derivatives and the functions themselves all have the same form. So that's why we have to use these things for undetermined coefficients. So for example, g of x could equal 5. You could have g of x equals x squared plus 3x plus 2. G of x is sine of x plus x cosine x. G of x equals e to the x cosine x plus 3x minus 1. Any of those will work. This one I would not, that one doesn't look nice. G of x equals natural log of x. G of x equals square root of x. G of x equals inverse tangent of x. Will not work. With undetermined coefficients. For these, that we'll talk tomorrow about variation of parameters.
Why wouldn't square root of x work? Isn't that just the exponent?
But when we take the derivative of square root of x, we get 1 over the square root of x.
Okay.
So we don't get the same function back.
Oh, okay.
But with a polynomial, we always get, when we take the derivatives of polynomials, we always get exponent, our variables to positive exponents,
Okay.
or 0 exponent. Yes?
The other three functions, like tangent, secant?
No.
Okay.
Because, yeah, when we take the derivative of tangent, we don't get a tangent back. And because we said a finite sum or product of these, our book doesn't include it, but you could include our hyperbolic trig functions. because the derivative of sinh and cosh is, well, not all hyperbolic derivatives, sinh and cosh, because the derivative of sinh and cosh is sinh and cosh. But those are exponential functions. Those are also exponential functions, so you can think of them either way.
But they wouldn't all work.
No, because we need, when we take the derivative, we need to get the same function back eventually.
Okay. Oh, because for tangent you get sec squared.
Right. And same for sine and cosine. When we take the derivatives of sines or cosines, we get sines or cosines back. When we take the derivatives of sinches and coshes, we get sinh and cosh back.
Yeah.
But the other ones, we don't get the same functions back.
Okay.
All right, and again, we choose these kind of functions because the form of the function is the same as the forms of its derivatives, of their derivatives. So, I would say we need to make sure your algebra and your differentiation is on point for this method. So let's look at an example. Well, we're good. I mean, we're good at taking derivatives, and we have had a lot of practice using algebra. I'll put it that way.
Yes,
Um,
we have.
So 2y double prime plus 3y prime minus 2y equals 14x squared minus 4x minus 11. So our first step always is going to be to solve the homogeneous equation. I'm going to say homogeneous auxiliary equation. For the homogeneous equation, we're just assuming that this is 0. So our auxiliary equation is 2m squared plus 3m minus 2 equals 0. And so we get 2m minus 1 times m plus 2 equals 0. So m equals 1/2, or m equals -2. So our complementary solution, y sub c, is c1 e to the x over 2 plus c2 e to the minus 2x. Now for our particular solution, we're going to assume y sub p is, since this is a second degree polynomial, we're going to assume that the particular solution is a second degree polynomial. Ax squared plus bx plus c. Because when we take the first derivative, we get a polynomial. When we take the second derivative, we get a polynomial. And our original function is a second degree polynomial. Now we're going to take some derivatives. Y sub p prime is 2ax plus b, and y sub p double prime is 2a. And we might be able to predict what's going to happen now. Now we're going to substitute. And we get 2y double prime, 2 times 2a, plus 3 times y prime, 2ax plus b, plus, or sorry, minus 2y. And this has to equal 14x squared minus 4x minus 11. Well, I'm going to distribute and gather my x squared terms, gather my x terms, gather my constant terms, and I get that negative 2a x squared plus 6a minus 2b x plus 4a plus 3b minus 2c equals 14x squared minus 4x minus 11. This, what does this kind of look like? It kind of looks like partial fractions.
That's what I was afraid you
But
would
it's
say.
easier. Because you
No,
can figure out
there's
A is
one
immediately.
Well, for this particular one, yes. So we get, so we equate our coefficients. So we get negative 2a is 14. So that tells us a is negative 7. We get 6a minus 2b equals negative 4. And we know what a is. This tells us then that b is negative 19. And we have 4a plus 3b minus 2c has to equal negative 11. And we know a and b, so this tells us that c equals negative 37.
That wasn't that bad.
Yeah, this one's not too bad.
Uh-oh.
So y sub p, our particular solution, is negative 7x squared minus 19x minus 37. And our solution, y, is c1 e to the x over 2 plus c2 e to the negative 2x minus 7x squared minus 19x minus 37. And if we had an initial value problem or a boundary value problem, we would substitute, take derivatives, and solve for c1 and c2. And as you might imagine in that case, we're taking the first and second derivatives of this whole thing. So solving for the constants involves a little more algebra. All right, let's look at another example. Questions here. Really, honestly, in my opinion, the difficulty in this method is sometimes in the derivatives and then just doing this process. Because if you have, depending on the functions you have, taking the first and second derivatives just involves just a lot of stuff. All right. 4y double prime minus 4y prime minus 3y equals cosine of 3x. So our homogeneous equation, sorry, the auxiliary equation is 4m squared minus 4m minus 3. I get equals 0. So this factors 2m plus 1 and 2m minus 3. So m equals negative 1/2, or m equals 3/2. So we get our complementary solution, c1 e to the minus x over 2 plus c2 e to the 3x over 2. We're going to assume y sub p is a cosine 3x plus b sine 3x. We need to include the sine because the derivative of sine is cosine. And we have derivatives involved. And now we're going to take derivatives. Y prime is negative 2a, sorry, just 3x. I want this should be 2x, sorry. I did it with a 2, so I don't want to redo it with a 3, because I have the algebra all worked out.
Can we ever do that on a quiz or a test?
Just say, oh, I don't like this number.
Yeah.
I had the algebra worked out for different problems.
This is the solution to the problem with this.
I like it when it's y equals 0.
this equation with these constants. All right, so now we're going to substitute. And we get 4 times negative 4a cosine 2x minus 4b sine 2x minus 4 times minus 2a sine 2x plus 2b cosine 2x minus 3 times a cosine 2x plus b sine 2x, and this equals cosine 2x. Well, when I simplify, distribute, gather my sine terms and my cosine terms, I get negative 16a minus 8b minus 19a. I added another. I didn't simplify my terms. Minus 8b cosine 2x, and this gives me plus 8a minus 19b sine 2x equals cosine 2x. So we know that negative 19a minus 8b has to be 1, and 8a minus 19b has to be 0, because there's no sign here. I solved this one for a. From this one, I said a is 19/8 b. That's what I did here. And I substituted. And I ended up with b is negative 8 4/25, and a is negative 19 4/25. Yeah, we get some big numbers on that one. Thank you. And so I'm going to just write our solution here. We get c1 e to the minus x over 2 plus c2 e to the 3x over 2 minus 19 4/25 cosine 2x minus 8 4/25 sine 2x. All right, so let me show you a table here to talk, the table that gives you some ideas about how what we need to assume for our particular solution based on the form of our g of x. And this is also, this is in your book in section 4.4. I don't usually use the table, but it can be helpful when you're getting started. I'll get us capture and stick it into our notes here as soon as we catch up. So we did an example of polynomial. So when we have a second degree polynomial, we assume our particular solution is a second degree polynomial. Third degree polynomial, we assume our particular solution is a third degree polynomial. We did a trig function. So for sines and cosines, we assume a sum of sines and cosines. When we just have an exponential function, we just assume our particular solution is an exponential function. But if we have products, we have a linear equation times an exponential. We assume that that's the form of the particular solution. Here we have an x squared e to the 5x. Well, that's a second degree. X squared is a second degree polynomial. So we assume that the particular solution is the sum, or the product of some second degree polynomial times e to the 5x. If we have exponentials times trig functions, we assume same product, but sines and cosines. Here we have a product of a second degree polynomial and a sine. So we assume that we have a second degree polynomial times a cosine plus a second degree polynomial times sine. This all goes all the way to g. We'll use a lot of the alphabet. Here we have x e to the 3x cosine 4x. So we assume that our particular solution is a similar kind of product. Yes?
Can I ask why it skips?
Yeah, why don't
It goes A, B, C, D, F, G on every single column. Number 4 on the left side, and then the bottom on the right.
So there's a method, I think this is why, where you can use capital D as a differential operator. So it implies taking derivatives.
Okay.
So that's probably why in this book they use a capital D for that operator. So you might confuse, if you saw a D there, you might think, oh, I'm taking a derivative. So that's probably why they skipped D.
It just seems a little funky.
Right.
It's just A, B, C, E.
So this gives you an idea of the types of particular solutions that you assume based on what you see for your function there on the right-hand side of your differential equation. All right, so let's look at one more. Y double prime minus 8y prime plus 20y equals 100x squared minus 26x e to the x.
Why? That's not bad.
So homogeneous equation. So we're going to say m squared minus 8m plus 20 equals 0. This doesn't factor, so we're going to use a quadratic formula. We use a quadratic formula for this, and I get 4 plus or minus 2i. M equals 4 plus or minus 2i. So our complementary solution, C1, e to the 4x cosine 2x plus C2 e to the 4x sine 2x. We're going to assume y sub p, this is a nice function, ax squared plus bx plus c plus d e to the x. I'm using d here. Will be okay. Plus ex e to the x. Because we have a linear function here, I could write this as d plus ex e to the x. So since this is a linear function, I'm including a linear function here. And when you get these kinds of functions in your solution, that's when the work gets particularly long. You have x cosine x and x sine. When you're taking derivatives, you have to use the product rule. So we're taking some derivatives. Y sub p prime. These are not bad. 2ax plus b plus d e to the x. That's not bad. Plus e. And when we take the derivative of x e to the x, we get x e to the x plus e to the x. And y double prime, we get 2a plus d e to the x plus e times x e to the x plus e to the x plus e to the x. So we have 2 e to the x.
Can we use F instead?
What happens if you make it for all the letters?
Now we're going to substitute.
Do the Greek alphabet. And you do so
I'm going to skip a couple of steps here when I substitute. I'm going to substitute, and I'm going to combine my like terms. When we substitute, we have 20a x squared plus negative 8a plus 20b x plus 13d minus 6e e to the x plus 13e x e to the x plus 2a minus 8b plus 20c equals, I need a little more room here, 100 x squared minus 26x e to the x.
Are you going to give us something like this on the homework? I see a lot of every single one of them. Why are you looking so deviously?
Every other odd.
What happens if you get a third degree polynomial?
Can't wait for
Or like a third degree differential?
That's a lot of work. It's a lot of work.
Can I write lots of work?
The answer.
I feel like you should give us one where it uses every letter in the
On our coefficient on the x squared, we get 20a equals 100. That one's not bad. We've already gotten one of our coefficients. How many do we have? 5?
Only 5.
So a equals 5. On the x term, we get minus 16a plus 20b equals 0. So we get b right away.
Where are you getting the negative 16?
Not b equals 0. b equals 4.
Um,
Did I?
Yeah, it's minus 8.
this is
Minus 8.
Yeah.
It doesn't
Yeah, 'cause it
matter.
was fives.
I mean, it does.
Oh, wait, it does?
It just like changes your B.
Oh, yeah.
So what do we have?
Or the A0.
Minus. No, that's correct. This should have been negative 8, right? Because we get negative 40a plus 20b. So b should be 2. Is that right? See, I already found a mistake in my arithmetic. I thought I was doing really well. On x e to the x, our coefficient on x e to the x, we get 13e equals negative 26. So e equals negative 2. On e to the x, our coefficient is 13d minus 6e, and that has to equal 0. This is 13, yeah. So we get D equals negative 12/13.
Hold on, what's the last one?
No, then you do 2a minus
And then on our constant, we get 2a minus 8b plus 20c equals 0. So I might need to redo this one because I had b wrong. So we get 2a is 10. 10 minus 16 plus 20c equals 0. So 20c equals 6. C is 3/10. So finally, and I condensed some of the steps here. Y is C1 e to the 4x cosine 2x plus C2 sine 2x plus 5x squared plus, is it bx? 2x? 2x minus 12/13 e to the x minus 2x e to the x plus 3/10.
Is there any unit in front of the sign to it?
I wonder what it looks like.
Oh yes, e to the 4x.
Can we drop this?
Can I see what it looks
What is
like?
it also weird?
Yeah, I have no clue what that
Yeah, like you want to see what it looks like.
I mean, what the X
I mean,
squared?
get rid of the C1 and C2 because we don't need those. I mean, I kind of like to see. Like,
Well-
let's just pretend that they're both 1.
Well, wouldn't like the e to the 4x
Because we
over
make our
power,
own conditions whatever we want.
wouldn't it eventually go exponential?
Well, yeah, as x approaches infinity, it's going to get bigger and bigger and bigger.
I think it's. I don't think it's gonna go negative like at all.
Oh, not Desmos?
Oh, you want to do Desmos?
I mean, we can do Wolfram Alpha if it's better.
No, I just always go to Wolfram Alpha.
Like, how can you argue with beautiful free math? Yeah, the colors. Do you want us to read it out to you?
Yes.
Okay, e to the 4x cosine 2x plus e to the 4x sine 2x.
Oh my lord.
It's already cursed.
Well, the sin x will balance it all out. Right?
Okay, plus 5x squared.
This is
Nope.
gonna be nothing. Oh wait.
Plus 2x
Just starts awesome.
minus 2x e to the x.
Because the sin is the first.
Wait, isn't that 12/13?
No, minus 12/13 e to the x.
Oh, yes.
It's just oscillating with
Plus 3/10. That's it.
But it,
Oh, so what is?
doesn't go.
Oh no!
I think it's oscillating.
Why
to
is there just like a
50.
random parabola?
Are there asymptotes, or are they just?
I'm not sure.
I guess it's like forever. Right, look, there's like a tiny little parabola on the left.
It's like they tried to draw
There's
a
one
parabola and they got
parabola.
mad at their homework.
Oh, see, this is that's an oscillation. It oscillates there.
What's in its motive?
What? Oh, it
Wait,
stops.
it stops?
No, it's because it's like
Yeah,
activating
I know.
so I can't get any of that.
You don't think so?
Oh, it's just a line.
Yeah.
A vertical line.
It's just a really nice line.
Yeah, it's zero.
X equals. Oh, it can only be so big. Like is it actually like a parabola? Or wait, no, it's exponential.
Yeah, because it's
right?
exponential, so it's gonna keep getting higher and higher.
Yeah, that's pretty crazy. And that's not a particularly terrible looking differential equation.
Oh, yeah.
Yeah.
I thought you were talking about the general solution.
Yeah, I
I'm like,
think that was one of the easier solutions.
All right, so the last thing for today is we run into a potential problem.
that's where we give up.
Did you already give us enough problems? I'm already having problems sleeping.
What are you gonna do about that?
Last night was having problems.
If part of our complementary solution is contained in our particular solution. Sorry, our part of our y sub p is contained in y sub c. So we have a repeat. So for example, in y double prime plus 2y prime equals 8e to the negative 2x. Y sub c, the complementary solution is c1 e to the negative 2x plus c2. And we would choose, we would assume y sub p based on this is a e to the negative 2x. But we already have that solution in our complementary solution. So this gives us a problem. In this case, anyone want to guess what we do?
You just add them, C1 plus A.
It has to do with reduction of power,
You add an X.
reduction of order. Yeah, we put an x in here. Choose y sub p equals a x e to the negative 2x. Yeah.
What?
Yeah, why not?
Oh, because technically it's
And
getting
it says
second.
you can choose
Right.
whatever you want.
Right, we can, because when you take your derivative with the product rule, that's how you end up with an e to the negative 2x. So, and this is true if we have any power of x already included in our complementary solution.
But then wouldn't y prime, no, okay.
I feel like it just would catch this.
I know. I was like, that's usually something Mr. Green would put on test and I would miss.
We include the next higher next higher power. So, if x e to the x is in y sub c, and that would be our first choice of y sub p. We choose y sub p equals ax squared e to the x. And that additional power of x comes from the reduction of order, if we want to think of it that way. So just be careful of that. If you have a repeat of your chosen solution for your particular solution in your complementary solution, you just have to put an extra power of x in front of it, or multiply by an additional x to raise the power, so they're not the same.
Honestly, not that bad.
Wait, what about other scenarios? like figure it out.
Yeah, you just look at the conflicts and say, okay, to avoid this conflict, I'm just going to multiply this by an additional, whatever, power of x squared, whatever,
Okay.
to get rid of that conflict.
Does it matter which x and x squared you put in which term? If you have multiple terms included,
So you multiply by the power of x that makes your particular solution not the same as your complementary solution. All right. Sharpen your pencils. Make sure you have a good eraser.
there's more than one word problem.
There's more than
I would think that would be.
Yeah, wait, how are there so many questions? Why are there
We're
so many
not doing
questions?
this with like the entire homework problem. Like you do that, and that's the whole problem.
Like, I'd expect like, like 5 questions.
Yeah, there's like
3 of like,
Maybe it just means it's.
Well, we have different scenarios for the functions, and we have some initial value problems.
we have 15 questions. This is like a chapter review.
And I'll be honest, when I do these, when I'm done,
I know.
unless it's an initial value problem, I just write, I just find the constants and stop. I often don't write out the entire solution. But if you have to solve for C1 and C2, then you have to write it out, then you have to take the derivatives. So tomorrow we'll talk about variation of parameters, which will allow us to solve differential equations where our function is not one of these special ones that we talked about. And in theory, we can also solve equations where our coefficients on our derivatives are not constant. And we will see a return of the Wronskian.